Right. So today is lecture number 5. This is the first lecture on actual computational fluid dynamics. Till now, what we have done is first two lectures we did some introduction. I talked about what is CFD and what is the use of learning CFD, and then we moved on to some ideas in partial differential equations, because ultimately the goal of this course is to solve partial differential equations of certain kind that we have discussed in the previous lectures. So, there is a common form of the transport equation which could be transporting mass, momentum or energy, and then we also learned how to classify those equations mainly based on the behavior of the solution that we get out of them, because that helps us classify the solution or the solver techniques using CFD. Okay, the solution behavior of certain class of equations will help us identify the solution methods. So, the first one that we will start discussing about is called the elliptic equations. So, does anyone want to give an example of an elliptic equation? We have talked about it. Elliptic equation, Laplace's equation. Okay, so this is an elliptic equation. It has a diffusive behavior in steady state. So we have discussed this in the previous lecture. If this doesn't make sense, please have a look at the video of previous lecture. It's available on YouTube. So before we actually jump into how to solve these equations, let's talk about let's recall the aim of this course. So we have a domain. It could be this room in 3 dimensions, and I want to solve for certain unknown or dependent variable. So that variable could be, let's say, phi as a function of x and y. In this case, it's a 2-dimensional situation. It's much easier to draw a 2D situation on a 2-dimensional surface, but you could think of it as a 3-dimensional domain like this room, and you're solving for, let's say, temperature in this room as a function of space and time. So it could even be a function of time. But for now, let us keep things simple and let's say it's only a function of x and y. So it's a steady situation. So I want to solve for an unknown phi in this domain. So this is a domain, and phi will, let's say phi is continuously distributed in the domain. There is no discontinuity for now. So I would be able to find out a value of phi at each and every point in this domain. That's realistic situation that you would have. But in CFD, as we have discussed, we satisfy ourselves by saying that I'll just find the value of phi at certain discrete points in the domain, and these points are called the nodal points. So we generate a grid or a mesh, could be of any type. I'm just drawing one Cartesian mesh which looks which is much easier to draw. So I draw some sort of a mesh which is just x and y lines, and each intersection point is called a nodal point. So node of mesh or a vertex of this mesh. So we will satisfy ourselves by finding phi values at these mesh points. So we will call phi i's, where I goes from 1 to n, where n is the total number of nodal points. So if you have, let's say, 10,000 discrete points in the domain, so you are happy with finding out the phi values at those 10,000 points only. Now, if you want to find a phi value somewhere in the middle of let's say, or somewhere inside this mesh element, what you can do is you can use ideas of interpolation. So, there are different methods available, that is something we will discuss later if required. But for now, the aim is how to find these phi values at these discrete node points. Okay. So, we have a continuous phi as a function of x and y, but in CFD we only solve it for discrete phi values. So phi at discrete points xi comma yi. So each node point has coordinates, let's say a general coordinate is xi comma y. Okay. So we will call these discrete phi's as phi i's, where I goes from 1 to 1. So that's typically what we are doing in this course. We are trying to find the value of phi at these discrete points. Is that clear? But the question is, how do we do that? This is something that we will be doing, but how do we do it? So what are we starting with? So typically what we start with, as we have discussed in the last few lectures, is a differential equation, a partial differential equation. Now how do we get that equation? That's through modeling. Okay, so you see a physical phenomena, you write the using the physical laws of motion, let's say Newton's second law, force equals mass times acceleration, and then that results in certain mathematical equation where the unknown phi appears that you can solve for. So we call it a governing differential equation. The one, let's say for example Laplace's equation, and that's an example of a governing differential equation. So in 2 dimensions it will look like again, this is just an example, it could be any kind of equation, any equation. So this is what we are starting with. We have an equation with some boundary conditions and so on. So now this equation, if I solve analytically, if I could do it, I would get phi continuous as a function of x and y, but that is something I cannot do. So I need a framework or a method which allows me to convert this governing differential equation, which is valid for continuous phi's here. Okay, I need to convert it to some form where the unknowns are these phi I values. So some equation or set of equations where the unknowns are phi i's, because ultimately I want to solve for phi i's, right, in using CFD. So I should be able to have an equation for phi i's that I can solve for. So the first step that we will be doing is to convert our differential equation to an equation for phi i's. Now since phi i's are discrete in number, we call these set of equations as discretized equations or discrete equations. So this process is called discretization, and that is what we will be discussing today. So how do these equations look like? So let's say they could look like some constant a1 phi 1 plus a2 phi 2 plus b2, a2 phi 2 is fine, equal to c1. So this is a linear equation, right? The unknowns are phi 1 and phi 2. Now you could have another equation where you have b1 or b2 phi 2 plus b3 phi 3 equal to c2, something like that. So what will happen is you will see you will have a coupled set of equations. So you will have to solve this linear system of equations. So that is what we will get out of this process of discretization. Okay, is that clear? Right. So let's now quickly jump into the process of discretization. Now the differential equation that we had written in the previous lectures had derivatives up to the order of 2. So we had first order derivatives, for example we had del phi by del t, that's first derivative with respect to time partially. We had del phi by del x, del phi by del y. We also had second order, not in time. We had second order in space, so we had del 2 phi by del x2, we had del 2 phi by del y2. So, we had derivatives like this. So, what we learned today is how to convert these derivatives to difference forms, where rather than having, because see, computers cannot solve differential equations, they do not even understand what derivatives are, but they can do calculations. So, if we have equations like this, where you have a linear system like this, then you can solve them using computers, using matrix operations and so on. So, we need to learn how to convert these derivative forms to discrete forms. Is the pace all right? Okay. So, these are very fundamental ideas. I mean, you just know them and just stating them. There is nothing new that we have started yet today. So, today's agenda will be to convert these derivatives to discrete forms, that is, forms which have phi i's in them. So, let us start with the first order derivative, that is much simpler to handle. And to keep things even simpler, let us not talk about partial derivatives. Let us say we are dealing with a 1D situation, one dimension. So, there is only, let us say, x. So, then derivative will have this kind of a form, d phi by dx. Now, we all know what d phi by dx means. Okay, it is the slope of the curve of phi with respect to x. So, if you have a curve like this, and we have a point here, let us call this point xi comma phi I. Right. So, d phi by dx, now the first thing is d phi by dx has to be defined at a certain x value, because slope will change with x. So, let us say we are talking about this at some xi value. So, that simply denotes the slope at this point, the value of the slope, and this can be found out through this limit. So, what does this limit mean? I will exaggerate the picture here for understanding. So, we have a point, let us say this point is xi plus delta x. So, basically this interval was delta x, and the corresponding phi value that you get will be phi at xi plus delta x, or we can write that as phi I plus let us call it I plus 1. Okay. Now, this difference or this ratio is simply the slope of the line that joins these 2 points. Let us use a different color. So, you join the blue and the red dot and you get, okay, for a finite delta x value, is that right? So, that is the slope of this line, and what you do is you take delta x smaller and smaller, and you can actually do that if you have the curve available and you can play around with computers. You keep delta x smaller and smaller, and you will see that the value of the slope of the orange line will tend towards the slope of the black dashed line. So, this was a quick recap in calculus. So, what we will do is, now this is exact in the limit. So, what we will do is we will approximate. So, let us approximate the slope d phi by dx at the point xi, that is the this point xi, as this. So, do we see the difference between 1 and 2? Can somebody raise hand and highlight what the difference exactly is between 1 and 2?
Tending x to 0 in first case.
Exactly. So, in the second case, delta x is not tending to 0, it is finite. It could be small, but it is still finite, and that is the reason I have used an approximate sign. Because see, in computers your delta x cannot it can be small. You can make it as small as you want, as small as your computer allows in the precision of your machine, but it cannot be identically 0. It cannot be exactly, or when tending is always a theoretical idea anyways. So, it can be small. So, what we will do is we will say that this delta x is finite, but we will still be happy. It is an approximation. We are engineers and scientists, and we tend to make approximations which are as long as they are sensible, we tend to use them. So, this is an approximation that we are using. That is the reason we have used an approximate sign here. So, I will just highlight here that note the finite value of delta x here. Okay, so just to make things a bit more compact, now what I will do is, well, let us keep the approximate sign. So, rather than saying phi at xi plus delta x and so on, we will use the symbol I plus 1. So, phi I is the notation for phi at xi, and phi I plus 1 will then be for the next xi value, which is after a distance of delta x, just a notation. So, this will help us find out the value of derivative, well, approximate the value of the derivative at any xi point. Now, if I want to be specific about the different points on the grid, so this is again drawing phi versus x. So, you have a point, let us say here, which is x1, then you have x2, then you have x3, and these x1, x2, x3, x4 are coming from the grid, the nodes, okay? Because you it is a 1D situation. So, what we are doing is, rather than solving for all x values, we are solving only for these discrete values. That is the reason we will talk about derivatives at these points only, not everywhere. So, I can write d phi by dx at point x1 as phi at 2 minus phi at 1 upon delta x. So, this x1 corresponds to the xi. So, let us say this is x1. So, we are talking about a point next to x1 minus the point at x1 divided by delta x. That is what we did. We took a point which was forward to xi. So, this was xi. So, we took a point which was to the right of xi, and then we calculate the slope. So, for a general case, for an xn point or xi point, we can write it as phi n plus 1 minus phi n upon delta x, or if it was xi, it is phi I plus 1 minus phi I upon delta x. So, this method that we have just introduced to you to approximate the first derivative is called forward difference method. It's called forward difference because to calculate the slope at a given point, I am taking one point to the right, calculating the phi value there, or finding the phi value there, or using the phi value there to calculate the or to evaluate the slope. So this orange line on the graph is the forward slope, and this is used to approximate the slope of the black dashed line, which is the slope at that xi point. Okay.
सर जो आपने ग्रिड डिस्टेंस लिया है डेल्टा एक्स, बट ग्रिड मतलब हर बार बराबर नहीं होगी ना?
What do you mean हर बार?
That की the delta x should not be same every time.
You mean every time we run the simulation or we solve the problem,
So actually the
or everywhere in around x?
Yeah, yes.
Okay, yeah, you are right. I mean, delta x may not be homogeneous. Delta x may change as a function of x. That is fine. So in that case, typically right now you are right. I have assumed that delta x is homogeneous. But if delta x is changing with x, then what we do is we tend to write this as x1 delta x2 delta xn. So we define delta xn as the interval size between xn plus 1 and xn, the difference between that. But for now, we have assumed that our grid is homogeneous. So we can have multiple levels of complexity here, but just to introduce the idea, we are assuming, but let's write that. Okay. So our assumption, constant delta x or homogeneous delta x. So delta x is not changing with x here. Now given that we have a forward difference method, we can very well have a backward difference method as well. So let's understand that through the graph. So this is phi versus x. Again, we'll exaggerate the situation. So we have a point xi comma phi I, and to find this slope at this point, which this time is the blue line, I can also use a backward point. Xi minus delta x, which will have a corresponding phi value, which is phi I minus 1. And if I join these two lines, these two dots, the red one and the blue one, that gives me a slope which is slightly steeper than the blue line, which I want to approximate. Okay. Now again, in the limit that delta x tends to 0, this orange line will tend to the blue line, but that limit is not existing right now. We are approximating. So this method approximates the slope at xi as phi at xi minus phi at xi minus delta x upon delta x. Okay, so in the backward difference method, to find the slope of the curve at xn point or at the point xn, it will be phi n minus 1 divided by delta x. Is the pace all right? Now, is there any other method that we can have that you have seen to approximate the slope? Fixed delta x. Right now we are assuming delta x is fixed, it is not changing.
So sir, it is depending on grid. Now we can use the x1, like we are finding derivative at x1, then we can give a constant value delta x by 1.
No, that's what I am saying. So for this discussion today, we are assuming delta x is not changing with x. every interval is of the same size. So my question is, we have learned two methods of discretization of derivatives. One is forward difference, one is backward difference. Can you think of a third one? Average of the two, center difference. Do you think that will be much accurate than these two? Center difference method. Let's use the same, let's do a different one, it's okay. So again, blue is the point xi comma phi I. So blue slope is the one that we want to approximate. So what I'll do is I'll take one point forward, which is xi plus delta x, and I'll take one point backwards, which is xi minus delta x. So the corresponding phi I would be phi I minus 1, and for the right point the phi I would be phi I plus 1. Now what I do is I join the green and the red dots. Can you see that the orange slope is much closer in value to the blue one? I mean, in this situation they almost look like parallel, so the slope is the same. So we are able to approximate the derivative better, intuitively speaking. So how do we write this? d phi by dx at any point xn is phi at n plus 1 minus phi at n minus 1, and what do I divide this by? 2 delta x, because now the interval size is between these two circles on the x axis. So that is xi plus delta x minus xi minus delta x. So the interval size is twice of delta x. You can see there are two intervals here. So this is called the center difference method. Is that clear? Any questions? Right, so couple of notes that we should talk about. So, the first one says the same derivative d phi by dx at any given point xi can be approximated in many different ways, as we have seen. So, we have seen three methods today. One is called the forward difference, others called the backward difference, and the third one was center difference. There could be others. Okay, so they are all so different methods can be used to approximate the same derivative in this method. Second note is each approximation gives a different result. Now, that is very important, because we saw that the slope, the blue line that we have that we are approximating, if you take a forward difference, you get an underestimation of the slope. If you take a backward difference, you get overestimation, and if you take a center difference, you get a better estimation than the forward and the backward difference. Now, see, I mean, overestimation is just for this curve. If the curve was different, you could have different biases, but the idea is that they will give different results. We have to remember that. And the third note is to understand why is there a difference. The difference is because the interval size is finite. If delta x was tending to 0, all these three slopes will tend to the all these three approximations will tend to the exact slope value. Okay. So, this error is there, error as in between the exact slope at the point and the one that you are approximating, that error is there because of the finiteness of delta x. That is a very important idea. It is quite simple, but still important. So, delta x is finite, and that is the reason you get an error in the estimation of slope. Okay. And this error has a name, it is called truncation error. So, the truncation error for the finite difference method would be the slope value exact. Error is usually the difference between the correct value and the incorrect value or the estimated value. So, the exact value of the slope at that point minus the one that you are approximating, that is using the finite difference method. And we as engineers will want to estimate the error, because see, everything is approximate. I mean, in engineering you cannot be exact every time. Even if you make a part, there is some small amount of tolerance in it, right? So, but engineering is about estimating the error. If you can give an answer and tell what sort of uncertainty or tolerance or error is there in your answer, that is when you become a true engineer. If you just give a solution, you do not give anything about the uncertainty or the error in the problem, then you are as well as a mechanic. You could just make a part which just fits and you are okay with it. Okay. So, we as engineers, we have to be able to quantify or estimate the errors. That will be the next step now. Well, let us have a fourth note, just to make sure we all remember the fact that as delta x tends to 0, all discretizations, and I am using the word should, now this may sound very obvious. Of course, I mean that is what we have seen in the forward difference, backward difference and center difference. If you take the delta x limit to 0, they all will tend to the exact slope at the point xi. Well, that is fine, because these are very basic ideas, but what happens is when we propose new methods, we propose discretizations which look quite complicated. So, there has to be a sanity check in that complicated expression, and we propose expressions because sometimes what happens is, for these simple expressions, for example, things may not work numerically. You may see a numerical divergence, some numerical artifacts which result in the numerical method not converging. You will get not a number. So, you have to play around with ideas so that your method becomes much more stable, so to say. But in that process of introducing stability, we forget about the basic ideas that your method should be consistent. So, this idea is called consistency. Well, that is the most fundamental idea. If you are taking the limit delta x tend to 0, your discretization should tend to the exact value of the derivative. And sometimes we actually live with non-consistent schemes because they are much more numerically stable. So, we say that we will introduce an error knowingly by giving a scheme which is non-consistent or inconsistent, but it does at the benefit of being able to get a method which is much stable numerically. We will talk about these ideas later in detail, but you should remember the word consistency. Okay. So, these three schemes that we have talked about, forward difference, backward difference, center difference, you can see they are all consistent. Well, you can see that through the idea of these intuition through slope, but I will show you that now mathematically, because that will be the part where we are able to quantify the errors. How many of us have never seen Taylor series? Everybody has heard about Taylor series. It's introduced as a part of mathematics course here. Okay. So, this is Taylor series. Taylor was quite instrumental in developing the field of CFD. He was the first one where these ideas started, I think in the 18th century. Brooke Taylor. So, Taylor series, let us understand before we understand the mathematical form, let us understand what this is giving us. Now, it is a very strong idea. So, what it's telling us is that if you have a curve and you have a point xi at which the function value is phi I, and you want to find the value of the function at a point which is slightly to the right, let us say for now, of xi point. You can do that. I can find the function value here by using the function value at xi point and using the values of all the derivatives of the function at xi. Quite an amazing idea. I mean, you are trying to find the function somewhere else, but you can do that by finding the function to the left of it using the function value at that left point and all its derivatives. Now, again, if you have an understanding of the series, you will be able to have an appreciation of it intuitively. It is a continuous phi. All the derivatives are defined. So, phi is infinitely smooth here. If it is not there, then you cannot have all the derivatives calculated at the point xi for phi. Okay. So, whatever I spoke, I have written that. It's an important idea, so I just wrote it so that when you revise these slides as a PDF, this should not be missed. Right. Now, this point xi plus delta x is mathematically speaking in the neighborhood of xi. Now, I will not define this idea. Okay, it's either it has been discussed in your mathematics course. It's a very mathematical idea, but again, let's have a hand wavy feel for it. It's nearby, pass mein. Okay, it's not very far away. If it's nearby, then I can easily find the value of the function at that nearby point xi plus delta x. I can find the function value there using the function value at the left point and its derivatives at the left point. Now, if delta x was very large, this Taylor series maybe could not be applied. So, usually the understanding is delta x is small, that is xi and xi plus delta x are nearby points. Now, there are certain functions where this is true for any value of delta x. Anybody knows what is the name of those category of functions? There are certain kinds of functions where you can apply this series for delta x being very large, or actually it could be infinite in size. Analytic functions, they are called analytic functions, where this Taylor series can be applied for delta x even as large as infinity. Exponential function is analytic. If you think about it, you will understand what I mean. But again, for this current discussion, xi and xi plus delta x are nearby points. Okay. So, let us apply the idea of this Taylor series for the forward difference method. So, we will use the Taylor series to find the truncation error in the finite difference, in the forward difference method. I do not want to write the series again, so I am just showing you the series on the top. So, forward difference was xi plus delta x minus phi at xi divided by delta x, right? That was forward difference. So, what I have done is I have taken this term on the left hand side and divided by delta x. That will give me the derivative approximation for the forward difference method. And remember, this is exact. There is no approximation here, do not get confused. This infinite terms here, it is exact. So, if I play around with this equation number 1, I can get this. On the right hand side, we will have d phi by dx at xi. Delta x is gone because we have divided the whole thing by delta x. So, the power of delta x will reduce in each term now. And there are other terms as well, we do not need to write them. So, what was truncation error? Truncation error was d phi by dx at the point xi exact minus d phi by dx at the point xi using the forward difference method. Right. So, this is the d phi by dx using the forward difference method. So, what I will do is just call this xi minus, and then you have all this. Let me write one more term. Is that clear? Just mathematical work, nothing else. Now this first term that we have, we call it the leading error term. Remember we said that delta x is typically small. We are talking about situations where delta x is small. So let us say delta x was 0.01. So the order of the first term is 0.01, assuming that the order of the derivatives is some constant order. The second term that you have has a delta x squared. So that order becomes smaller than the first one, right? It's of the order 0.0001. And if you go higher terms, delta x cube, it will be much smaller. So if you add a small term with a much smaller term with a much smaller term, you can approximate that as a small term. If you add 0.01, 0.0001, 0.00001 and so on, you can approximate this as 0.01. Let's say you are happy with 2 decimal, 3 decimal places, right? That is the reason we say that we can approximate this whole thing as just some constant times delta x. That constant takes care of 2 factorial derivative and so on. But typically the order is of the order of your interval size. Remember what we are doing here is estimating the error. So if your estimation of error has multiple terms in it, the summation is dominated by the first term, which is called the leading error term. So we say that the forward nothing error can be positive error or negative error. So usually what we do is when we talk about error we take the absolute value. Okay, negative sign is not showing anything because you see the slope could be positive or negative and so on. So in errors negative sign will not show us anything. Errors typically are how far away you are from the exact solution. That's pretty much it. Okay. So in the forward difference method or we say that the truncation error is it goes as delta x. Even I can remove c. So I am sure you have seen this notation in your mathematics course. So if it goes as delta x, that means truncation error typically if you are estimating the value would be some constant times delta x. Constant could be anything, but as you change delta x, it will change linearly with that. So we say the forward difference method is a first order discretization. It's first order because your truncation error is going as delta x to the power of 1. It's a bit confusing. The order word here is for the error, not for the order of the derivative. Similarly, the backward difference method is also first order discretization. Any guesses on what center difference method would be? That is the truncation error in this center difference. It goes as delta x squared. So what that means is if you had control over delta x, and we have that, I mean if you have a very good computer, I can put smaller delta x value so that I will have lots of mesh nodes. So if you reduce the delta x by half, the center difference method will reduce the error to 1/4, whereas forward or backward difference method will only linearly reduce the error to half. So center difference is going to be much more accurate in terms of controlling the error by delta x. Okay, so there is a homework for you, and these homeworks are important because they will help you with the quizzes and exams. You have to show that the center difference method is second order. So you write Taylor series for, I plus 1 and phi at I minus 1. and then you can use that to get the error for center difference.
Sir, the quotient term in the truncation error.
You mean this one?
Yes,
Huh.
as a second order derivative. So we have to discretize for calculating this.
No, don't get confused. We are actually using a method which is this one. So in our equation, wherever we get the derivatives, the first order derivative of phi with respect to x, we'll replace that by this. But this exercise was to understand what is the order of the error in this approximation. Only order of error. Okay. So that, and we will show that in the lab. We will have actually a tutorial / lab on this Thursday. We'll meet downstairs. I'll let you know where. So there I will show you. I'll write the code in front of you, and I'll show you as we decrease delta x by half, the error will reduce by 1/4. You can manually do. You can check it in computers, but you should be able to understand that beforehand when you're developing the schemes. So this is called analysis of your method. So that is what we showed, that the error is second order accurate. That's all. We are not trying to. We will not find the error in our actual problem. Okay. So we'll stop here now, and I'll meet you tomorrow.